Is Chemistry 111 class, and the first thing we're going to do is read this article. It's about a new laboratory discovery, and after we read it, I would like you to summarize it in one paragraph. So this is Science News for Students, a science news website for students like you, and the topic here is chemistry. The title is Lab Creates a New Unexpected Type of Firenado. These tiny blue cyclones of flame could become the next best thing in clean combustion. So if at any point you don't understand what I'm saying or you don't understand one of the words, you can pause the video and look up these terms in a dictionary and take it slow. Researchers studying large swirls of fire in the lab have unexpectedly stumbled upon something new. It's a small blue fiery vortex. This tiny tornado of flame burns incredibly hot and produces very little soot. If these fires can be created reliably and controlled, they might offer a range of benefits. For instance, they might clean up oil spills in the water, and someday they might even play a big part in clean combustion of fuel in devices such as furnaces or hot water heaters. Fires can be devastating. They also tend to be largely unpredictable. Those are just two reasons why many scientists study them. These are the reasons why people study fire and why it's important to study fire. If researchers can figure out how fires behave, they might better predict where and how quickly blazes might spread. That could save lives as well as prevent property damage. One of the more fascinating aspects to wildfires is the fiery whirlwinds that suddenly spring to life within what seems to be a normal wall of flame. These fire whirls, known as firenadoes, can grow dozens of yards high, notes Elaine Oren. So this is actually a paraphrase of Elaine Oren, and it's introduced with the verb notes. Instead of saying Elaine Oren says, it says Elaine Oren notes. It's a common way to introduce a paraphrase. Here's an explanation of who Elaine Oren is. She is an aerospace scientist at the University of Maryland in College Park. Fire whirls are especially dangerous, she notes. Again, a paraphrase. And remember, this isn't a quotation, right? Because we don't have quotation marks. This is a restatement of what she said in this person's own words. She notes they can lift small bits of burning material high into the air. From there, the material can fly off to distant sites, triggering new fires. So, these fiery whirls are a topic of intense study in Oren's lab. So, this is why fiery whirls are interesting and important, and why she's studying them. She and her teammates create the cyclones of fire in several ways. In one setup, they pump a liquid fuel onto the surface of a small pool of water. That fuel, called heptane, is a component of gasoline. When lit, this fuel evaporates, mixing with air. One part of the team's equipment guides air into an open-topped cylinder that surrounds the floating blob of fuel. This cylinder acts like a chimney. Incoming air creates a slowly swirling vortex inside the cylinder. As the burning vapors whirl and rise, they draw more air into the cylinder. This intensifies the swirling. Soon, instead of a rotating fire, there's a whirling firenado. In the lab, these fiery cyclones can be around 1 meter, about 3 feet tall. The researchers keep the firenado that size or smaller by controlling the fuel supply or on notes. So again, this is paraphrase of Oren. If it grew much larger, they might quickly lose control over it. Both the original blaze and the firenado that follows are loud. That's a sign that the airflow inside the fire is turbulent or chaotic, says Oren. So far we've talked about how they create firenadoes in general, the big ones. But during one experiment, the team's firenado shrank, became much smaller, and evolved, or changed, into a blue whirl of flame, just a few centimeters or a couple of inches tall, like this. We've never seen that before, she notes. Certainly, she adds, we didn't expect it. So I think what they're talking about is this right here. That tiny blue whirl was very quiet, and that was one clue that the air flowing inside the flame was smooth, not turbulent. Its blue hue also signals that this flame was much hotter than normal, maybe a couple of thousand degrees Celsius, a few thousand degrees Fahrenheit, rather than a few hundred. It also means combustion inside the whirl was not creating soot, the black, oily carbon that typically gives a flame a yellow hue. Besides burning hot and quiet, the little blue whirl was stable. We found we could keep it going as long as we fed it fuel, Oren said. It's a hungry little beast, and when the fuel disappears, the flaming whirl dies out quietly. After the flame was gone, the team tried to relight the water's surface, where the fuel had been, but nothing happened. This signaled that all of the fuel was gone. Any remnants had burned away, evaporated, or sunk. Floating oil spills cause huge problems, notes William Roberts. And again, they're using the same verb, notes, to introduce the paraphrase of this person. He's an aerospace engineer who was not part of the research team. Roberts works at King Abdullah University of Science and Technology in Thual, Saudi Arabia. The oil from a spill can wash ashore to poison beaches and coat birds, he notes. Lighter gases or liquids in the oil can evaporate, polluting the air. The gunkier parts left behind will sink, fouling the ocean floor. Plus, it's really tough to recover spilled oil, even where it can be collected. It usually can't be used, Robert notes. So again, we're talking all about what a scientist says. If people could find a way to create and control blue whirls, it might be a way to burn spilled oils cleanly, he says. And here we have a quote, his exact words. Okay? He says, "The team's discovery shows the importance of doing lab studies of complicated phenomena such as fire," Roberts adds. So this is kind of like the discussion, the significance of what they have found. So this is how floating oil spills could be addressed by this new discovery, right? Plus, it's really okay, right. So here we go. The team's discovery shows the importance of doing lab studies of complicated phenomena such as fire, Roberts adds. It's that sort of looking that causes you to find things like blue whirls, he observes. This is something really cool. Now let's figure out why it works and how we might be able to harness it, right? So this is a discussion of the results, like I said. Jose Torrero is an expert on fire safety at the University of Queensland in St. Lucia, Austria. Fires of all types, whether artificial or natural, are very complicated, he says. Paraphrase. Within flames, all sorts of complex chemical reactions take place. There also are many ways for fires and streams of air to interact and influence each other. There are fundamental physical processes going on in and around fires that we don't understand, he points out. If we understood them better, we could better forecast how fires would behave. Again, discussion of the results and their significance and their importance, and a blend of paraphrasing and quotation, which are exact words. Of course, you'll notice this article doesn't have in-text citations, like you've learned about in your NQ Spirit class. And by in-text citations, right, we mean like stating the sentence, right, and then you have your citation in parentheses with the last name and the year, if it's APA style, or if it's not APA style, then just maybe scientific style where they just have a number as a superscript or in parentheses. This doesn't have citations in the text because it's often news stories don't cite in the same way. But usually in any essay or article, you would have to put your citation right here at the end of the paraphrase or quotation. And remember, you have to cite for both paraphrases and quotations. Until that day comes, people need to keep studying fires in the lab and maybe stumbling across new and unexpected things like blue whorls. Okay, so you're welcome to read through this over yourself to better understand it. And here are some key vocabulary words that might be helpful for understanding the article. And here's a citation of the original science article. So before we go on, I would like you to summarize the article that we just read. Read the following article and summarize this discovery in one paragraph, which might be around 5 or 6 sentences. You might need fewer or more, depending on how long your sentences are. But try not to use very long sentences because they might get too complicated and you might not be able to express exactly what you want to say with a long, complicated sentence. They're also more difficult to understand. Okay, once you're done with that, we're going to look at the abstract, so just the summary, for the original research article that it was reporting. So let's look here. This was published in Proceedings of the National Academy of Sciences of the United States of America. Here's the title. As you can tell, it's more technical than the original one, right? From fire whorls to blue whorls and combustion with reduced pollution, instead of our original title, which was Lab Creates New Unexpected Type of Fire Tornado. Okay. This is the significance. You won't usually have this in an article, but this tells you why the research is important, okay? And here we have the abstract, which is a summary of the whole article, right? The topic, the importance, a summary of what was done and what was discovered, and a discussion of why the results are important or what can be done in the future. Okay, so based on this abstract and the original article, right, and the summary that you created of it, I would like you to answer the following questions. What is the importance of the topic? Why is the real what is the real world need that they're talking about? What research has been done so far and why is it insufficient? And you'll get a lot of this from the abstract if you don't understand yet. What are the results of the laboratory studies reported in this article? And what are the research and real-world implications of these results found? So you can really find the answer to these two questions in this article reported. And if you're having trouble coming up with answers to these two, then it's probably because you haven't read the abstract yet. So let's read this together, and then you can try to tackle those questions. All right. So fire whorls are powerful, spinning disasters for people and surroundings when they occur in large and urban and wildland fires. Whereas fire whorls have been, so this is like a general real world problem they're talking about, so you want to read it and understand it. Whereas fire whorls have been studied for fire safety applications, previous research has yet to harness their potential burning efficiency for enhanced combustion. So this is talking about the previous research and what's wrong or missing from the previous research. This article presents laboratory studies of fire whorls initiated as pool fires, but where the fuel sits on a water surface, suggesting the idea of exploiting the high efficiency of fire whorls for oil spill remediation. And if you don't understand this, it's really technical. That's okay, because they've explained what exactly they discovered, like these fire whorls sitting on top of water, in this article. So you can get your information from there. We show the transition from a pool fire to a fire whorl and then to a previously unobserved state. Oh wow, this is something previously unobserved, brand new. A blue whirl. Wow, they made something new in the laboratory. That's so cool. A blue whirl is smaller, very stable, and burns completely blue as a hydrocarbon flame, indicating soot-free burning. It means clean. The combination of fast mixing, intense swirl, and the water surface boundary creates the conditions leading to nearly soot-free combustion. Clean. With the worldwide need to reduce emissions, dirt, from both wanted and unwanted combustion, yucky, discovery of this state points to possible new pathways for reduced emission, cleaner, combustion, and fuel spill cleanup. Because current methods to generate a stable vortex are difficult, we also propose that the blue whirl may serve as a research platform for fundamental studies of vortices and vortex breakdown in fluid mechanics. So this is kind of like the real world implications for their results, and this is so pointing toward a future, and this is pointing toward a future for research. So you can see it follows the general format of intro, methods, results, and discussion of what the results mean, all compiled into this tiny itty-bitty dense abstract. And if you're really interested, you can go read the rest of the article. But what we're going to do right now is just answer these questions based on what you found in this abstract, right? Which is the same thing as this one here. I just copied and pasted it. And the original article, which makes the topic a little bit simpler for you guys to understand. So when you come to class next time, you should bring your summary, okay, and the answers to these questions, and we'll discuss them together. If you have any other questions, you can email me, and that's the class for this week. Remember to save your answers because you're also going to submit them on November 15th, I think it is, for your reflection booklets. Have a wonderful weekend and a wonderful week, and thank you for listening.